Mikael. Great, yeah, Gustaf.
To show it. Okay?
Yes.
Good. So this will not be as scientific as Sean's. Where's Sean? Oh, there. I'm going to present a library that I've been writing, which I think will cover the topic of functional reactive programming. It has a web page, of course, and it's on GitHub. So in the world of fake news, let's get some facts, so you know that you can actually use this. It's fast, it has no dependencies, requires only C++11, is open source with Apache 2, which means you can use it in closed source applications if you like. And it runs on these platforms. So if your platform is not there, then yeah, pull requests are welcome. There was some people writing a game last summer who made it work for Android as well, because they have another C library, so some things are actually different. Even though we do C++, things like stack trace, and yeah, it's never as easy as just C++. So why have I written this library, and why should you use it? It allows you to write code which is functional-ish. And that's very important, I think. We should all try to write functional code rather than imperative. Asynchronous data flows and error flows are usually horrible to write. And I will show you examples of that code that maybe you do right now. That's the most important thing of this whole presentation, basically. If you want to use threads for parallelism, excellent. If you do that with Q, you will not need to use mutexes anymore, which is fantastic. And a little bit bold statement, maybe, but yeah, you might need to use mutexes if you actually do things in parallel with the same state. But usually, what you do with mutexes is to lock state that you move between threads, just in the moving process. And with Q, you don't need that. It decouples logic and execution, and it performs the execution, so you can write logic. And I will show you what that means in real life. So about functional. C++ is a functional language. Kind of. It depends. If you want it to be, it can be. Since 14, definitely you can write functional code. And some of you might have heard that the bugs are in the state. Yeah? No? Some? It's very true, actually. When you modify state, when you manipulate variables, that's often where bugs happen. It's not so often that you have less than or greater than or some other algorithmic stuff wrong. And of course, if you don't manipulate shared state between threads, then of course you reduce the risk of bugs even more. So I will focus on this for quite some time. Let's write a program as an example to show you. So this could be your program, but I'm going to make something quite silly. So we built a chat app, and we have logged into some server once and got some token back, so we can reuse this. So we read some token from disk, and then we ask a server, hey, are we still valid as chat member? Yes, no. And it replies maybe yes, or no, you have not paid subscription or whatever. If everything's fine, we ask, okay, give me my unread chat messages. And then eventually it replies back. These two are inherently, they are synchronous because it's networking. And then we parse these messages, which might take time. At least you should believe that this is CPU expensive. Maybe we decrypt messages or decode MPEG or do something else which is a little bit CPU intensive. And then we present this or save this or something. So it's a silly example, but you will recognize your code probably here. Wow, slider. Fantastic. Well. It is what it is. It's not like this on my computer. So. This is how code looked a long time ago when we all wrote try catch and blocking code. You could do all of this in 5 lines. You call a function, you get the return value, you use that, call another function, and it blocks. Get unread messages, it blocks. Even though you ask some server something, which might take a long time, that thread is blocked. It's not efficient, it's not performant, it's not what we will do nowadays if we need to do these things, 10,000 of these concurrently. But the code is simple. Doesn't anybody not understand code like this? No, of course. But it's not performant, it's not what we do nowadays. If you need to do multiple things like this concurrently, you need threads. With the risk of deadlocks and everything. So, how would we do this asynchronously? Well, usually we do this with interfaces. Interface-based asynchrony. I will show an example of this. Nowadays we can use ad hoc callbacks, lambdas. Fantastic. Sorry, I'm making noises to the recording. This is better, but not much, actually. And nowadays you can actually use promises with this library. So let's look at how you do this with interfaces. You need an interface which will be these 2 functions, of course. Everybody understands that you need those 2 functions for the previous example? No? No, neither do I. But you do. Because we need to extend this interface in the class. Yeah, so the old example was nice. This is how you do it with the synchronous programming. Because we can fetch the user from cache, that's synchronous, fine. We need to save the state somewhere. Why? Well, we'll see why. Then we call verify user token. This is asynchronous. So we call this function, and we say, hey, this. And this is a pointer to the class, of course. But it's also a pointer to the interface. And verify user token knows by some magic that somebody wrote that it can call a function do stuff part 2. So it will. This is how code actually looks in production, but you might have better variable names, I suppose, than function names. It's not very clear what's going on. Also, on which thread will these 2 functions be called? The part 2 and part 3. They will be called by someone. I don't know, some thread. What happens if we do something that takes time there? Good? Bad? No. It's not obvious here, anyway. Also, what if some of these asynchronous functions connects to a server and the server says, whoa, what's that? It's an error, we can't parse this. How is that function, verify user token for instance, supposed to tell us that it failed later, asynchronously? Actually, we need these 2 asynchronous functions, or functions that will be called in a while, to be able to get not just the value, but also an exception. So the exact code, you don't need to kind of study it. There might be compilation errors. Yeah, the first function doesn't even have a return type. Well, it doesn't matter. It gets quite big. What if you throw an exception in any of these 2 functions, the last 2? They're called by some function. And you're throwing an exception. What does that mean? That's not very nice. It's like you ask a friend for help, like you're going to move in the weekend, and the friend helps you to move furniture, and the last thing you do is you hit your friend. That's not nice. That's exactly what you're doing. You're saying, hey, Mr. Get Unread Messages, please give me messages. And it does. And it calls do stuff part 3. And you're just throwing something back. So to write code like this, we need lots of try-catch, lots of exception handling. In every single function, we need to handle exceptions. It looked like this before, in the old days, when we didn't have so much asynchrony that we need nowadays. Usually, I'm expecting that we need more asynchrony now. I think we do. So that's a problem. So nowadays we can make a few of these things better. We can write the whole flow. These scroll bars. We can make all of the whole flow in one function. So this is inside a function. And when we need to do something asynchronously, we call oh, I have a mouse. We call this function with a value, and then we provide a lambda function, which will eventually be called. And then we can capture state, which has to do with this particular flow in the lambdas. It looks better, it is better, but you still have the same problem. You need to handle exceptions everywhere. And anything can fail, so you need to, when this is called, do something useful, propagate this error somewhere. And this is actually called callback hell. It's not my name, but it's called callback hell. The whole code will look like a right arrow, like a greater than, with more and more indenting the more asynchronous functions you call. So with callback-based functions, you call a function, you give it some arguments, and the last thing you do is you provide a callback function, usually. With promises, yeah, sorry. The callback needs to take a value or an exception, because you don't know if it fails or not. But we don't have space for it, so I'm going to just ignore this here. With promises, you don't get scroll bars. So with promises, you call a function with the arguments that it needs, and nothing else. And it will return a promise of something, which is the future value. So promises is called promises in my library. It's called other things in other libraries, in other languages. But it's the same thing. Futures, asynchronous tasks, so on. So by returning the future value instead of forcing you to deal with it in a callback, what can you do with the promise? Well, what can you do with an object? I mean, you can ignore it, you can return it, you can call a function and say, hey, take this promise. You can treat it like any other variable. And you can pass it to the part of your code which is responsible for that future value. In the callback, you have to deal with whatever happens when that callback is called. Well, you need to do something at that time. When you get the response from network, you have to, I mean, your function will be called, so you cannot like delay a function. Here you can delay caring about the future value, and I will show you why. So we had three functions. Let's say they're asynchronous. They take an argument and a callback, which will be called eventually. I have to remove stud : because there's no space. Breaks my heart, but I have to do it. Yeah, some of us are quite strict on stud : the functions, the same functions would look like this if it's promises. So they return a promise of the future value. Okay. These scroll bars. Anyway, so this is what we did. We call a function with value, provide a callback. How would you do the same thing with a promise? You call a function and you get some promise back. How do you get the bool eventually? Well, a promise has quite a lot of functions. One of them is called then. So we say, when this promise eventually becomes a bool, then call this lambda function. So they look quite similar, I would say, but they are very different. On the right side is exception stating, for example, which is nice. Now get unread messages is also asynchronous, so we also need to provide another callback for that one. I won't have space for exception pointers, so I'm just going to ignore them. How would that look with promises? Well, what does then return? Then returns another promise. Of what? A promise of the type that the last promise returned. So get unread messages returns messages, or a promise of messages. So then we'll return a new promise. What can you do with a promise? Well, you can call .then. Simple. This function is also asynchronous, so it keeps going. You see the greater than angle, and it's complete fake news. I mean, you don't handle exceptions that functions throw to you, and you don't handle exceptions that you might by mistake throw back, punching a friend. But on the right side, that is actually handled. I will show you that in 2 slides. These last 2 lambdas, they don't capture anything. They just call a function, so they are unnecessary. We can simplify that as this. If you can So, about exception safety. Let's say get 100 messages throws an exception. Synchronously, or eventually it couldn't parse whatever the server replied with. What would happen? Can we call the next functions? No, it makes no sense. So we need to exit success flow, go into some kind of error flow until we have a catch handler, and then do something useful. Retry, quit the program, whatever. We do that with try catch usually, normally with synchronous code. With promises we do this with fail. You don't see very well. You don't need to see very well. If any of these above functions fail, any of them, the ones below will not be called. Instead, the function that we call error handler will be called. And this looks familiar to something. This is how code looked 20 years ago. It looks the same today, of course, but we don't write as much synchronous blocking code nowadays. Again, like, do I need to explain anything? I don't think so. You can catch specific types of errors. You should know this. Otherwise, now you know. With Q, you can do the same thing with the synchronous code. Looks the same. Is the same. Then auto, fail, catch, tomato, tomato. You can catch specific errors as well. So it's the same thing, but the right side is like performant. You can do many of these concurrently on one thread. And this is because Q decouples logic and execution. So Q is executing. Q is calling these functions, handle, result, do more stuff, yet more stuff, yada yada. Even the fail handlers, of course. And since Q is calling your callbacks, you can throw, and it will catch whatever exception you throw and propagate it down to the fail handlers. So far, are we good? Obvious, trivial, of course, yeah. I would like to see the next slide, but we don't have separate screens, so I don't know what's coming. Threads. That's cool. I said we can use parallelism without mutexes. Did I lie? Yeah. No. We need to look at some parts of Q of how we actually execute things. So there are two things here which you see, Q and event dispatcher. There's something else I won't mention. It's there for correctness. So event dispatchers are things that call functions. They work, they do things. And you have two built-in ones. You have a blocking dispatcher. So you can create an object which is a blocking dispatcher, and you run the function start, and it just hangs there, blocks. And it can perform functions until you somehow stop it, and then it runs through. And you have a thread pool. And you can build any ones you like. You can build your own bridges to Windows 32 or any kind of event loop or network loop or what have you. Why would you do that? Well, all the callbacks, like these then things, that Q will call, on which thread will it call those things? Well, internally, they're called tasks. So the tasks will be put on a queue, and the queue is a queue. You can put many things into it, and they will be pulled by the event dispatcher and then eventually executed. So now we know this. You need to kind of know this to understand some of the rest. So let's build a program. What do we begin with? Int main. Don't look too closely if you're tired. It's not really relevant exactly what I'm showing in the next 2-3 slides. You need to allocate a blocking dispatcher and a thread pool, well, if you like. A queue which will correspond to the queue will be bound to the blocking dispatcher, the TP queue to the thread pool, so the names kind of make sense. You create the blocking dispatcher, you create the thread pool, don't care about what exactly what's going on, and then you start the blocking dispatcher. This is basically hello world with queue without printing hello world. And before you start the blocking dispatcher, this is a program that will do nothing and just hang until you do Control-C. So that's cool. So let's do something. So you need, before you start blocking main, you need to actually bootstrap your program. And you do that by maybe dependence injecting the queues. The queues are the key. We can ignore these the dispatch and mumbo-jumbo things. As long as we have queues, we're good. Why? Because all promises must have a default queue. And the reason for this is that if we create a promise, fantastic. This is really not something expected. That's fantastic. Do we have an editor?
Can you change the zoom and see if it appears?
You think so? How would you?
Control plus or control minus?
Of course not. But this is one line, and it looks like is it Control C? With QWith, you can take a variable and say make this a promise. So if you say QWith with a value 5 is an integer, so it returns a promise of an integer. And you can do then and say whenever this promise is actually 5, it's going to be 5 immediately, but we don't know. Then call this lambda function. This lambda function will be called on the thread corresponding to the queue. So that's why. Knowing this, we can finally parallelize without using mutexes. And this is the cool part. You saw this code before, lots of stuff, some asynchronous function calls. These function calls probably are called because we got some network response. So they're probably called from some I/O thread. And great with the scroll bar. This is CPU heavy, it says. This function is CPU heavy, it consumes a lot of CPU. And we call this function in a function that is called from the I/O thread. If we do this, we're probably going to block lots of other networking. So let's do what the title says. Let's offload this function, parse messages, to a thread pool, so we don't block other I/O. How would you do this with code like this? It's not trivial. It's like you need to package the value and the function, put it to some thread pool, and hope that it doesn't throw an exception. It's not trivial, I would say. I mean, it's not rocket science, but you need to know what you're doing. Same code looks like this if it's Q, without the scroll bars. It's the same thing, it's just that with Q, code usually gets like slightly smaller and exception safe. So this code, frustrating is increasing. We parallelize and we put parse message off to a thread pool by just specifying the queue as a second argument. So all these functions will be called on the same thread probably, except parse message, which will be called on a thread pool. So now we have parallelized the program. And where are the mutexes? There are no mutexes. Why are there no mutexes? Because there's no state that we modify. There's no variable here that I'm modifying, or no. And this is because it's kind of functional reactive. We react on previous asynchronous calls with then, and the code flow is functional in itself. This is nice. Quite often we need to wait for multiple things to finish, like you have a network request that you need to wait for, and you need to wait for some CPU intensive task running on a thread pool maybe. And when both of them are finished, then we continue to do something. Also not trivial to do usually with either interface-based or callback-based asynchrony. You need to allow any of them to finish first, of course, and build some magic box with all the states, lock that, do stuff, all that fun things. With Q, you use Q all, and then you're done. So let's say we have two mutexes. I'm going to create two mutexes just for fun. We create one mutex, which will be a string, a promise, which will be a string, and we create a promise, which will be two things, an integer and a floating point. We move them into Q all, which is a function call. And what does Q all return? It returns a promise of the individual promise arguments of these promises. Oh, wow. So the scroll bars are changing. That's excellent. basically, the promise it returns, we can do .then and get these string int float as synchronous values and work with them. So this function, the lambda function, will not be called until both promises are resolved, finished, done, complete.
So this could have been on two different queues.
Those two could have been, but when you do then, you need to specify a certain queue. Good question. In this case, it will actually use the queue from promise 1.
Okay.
But don't tell nobody.
Yeah.
Yeah, that's yeah. But you can change it by specifying the queue you like here.
Yeah.
So maybe this is something you do on a separate thread or whatever.
Yeah.
No mutexes. Oh no. I'm good with time. Fantastic. There is another part of queue which is not promises, which is channels. It's quite interesting because we all need to stream data in our applications usually. I mean, that's what programs do. They read things and they write things and they do some stuff in between. All programs. Tell me one program which doesn't. Except the CPU burning program. It doesn't exist. So you can, I mean, the channels in queue are like a thread-safe queue. How many are picking a thread-safe queue in their life? Ah, only me. Cool. One more. Yeah, one more. Which is, yeah, we've been there, done that, and it's not that obvious as you might imagine. And they have back pressure control, which is cool. I will show you what that means. Promise-based. Maybe that's good. Maybe not. You'll see. And they have sweet concurrency handling. It's actually very, very sweet. And they have more that I don't have time to show today. I mean, a thread-safe queue is basically a queue that you can push things in one end and read from the other from any thread. So when writing, you lock a mutex, you push something in, and then you unlock. Simple. When you read, you take the lock, take the mutex, you pop the first value, and then you unlock. Is that as easy? No, it's not. Maybe there's nothing to pop. What would you do then? We've all been there, those of us who have written thread-safe queues. It's like, what do you do? Do you return null or, yeah, whatever?
Stood abort.
What?
Stood abort.
Stood abort, yeah. Kill the program, it's worth it.
Yeah.
Yeah, well, why not? So to create a channel, it's like creating a vector, just channel ch. Simple. This is a channel int, by the way. Obvious. And you need to provide these queues again, all these queues everywhere. Yeah. Hence the library name queue. Actually not, but yeah, maybe. And then need to provide a certain backlog. How much should this queue, this channel buffer before it's like full, which is completely optional. You can fill it as much as you like and blow up the memory. Fine. But when you fill things up till the size of 10 in this case, then you can choose to respect back pressure and not push more things until you are being told to push more things. I will not show you how that works. It's a little bit tricky. The channel is quite useless in itself. You need to get some readable and some writable thing, which is objects. And you read from the readable and then you write to the writable. Duh. And reading from the readable, of course, returns a promise, because we don't know if there is something to read yet. Maybe later there's something to read. So consider this sweet interface. And write, you can write anything. Now when you read only one thing, the first thing in the queue. And this is asynchronous, so if you want to do this multiple times, you need to recurse over read. Of course. How do you recurse if you have asynchrony? You need a synchronous recursion. Does that term exist? I don't know. It's simple. You just have a lambda which captures itself. Yeah. No one is complaining. So yeah, maybe that's easy. That's not easy, but it can be done. But maybe you don't want to do that. So there's another way to consume things with scroll bars. With using consume, which will be called for every value. And this is the sweet concurrency handling in 2-3 slides. You say call the function on value every time there's something to consume from this channel. Okay, trivial. And then when the consumption is done, the channel is closed. then the promise that consume returns will be resolved and we can print done. Fantastic. But what about back pressure? Let's say that we can push things into this channel quickly. But consumption is something we don't want to do too frequently, too fast. Maybe we're saving something to a database, and if we just keep saving the words out of the database, it's going to, be slow, or we kill the database. We can't save a billion things at once, but we can stream a billion integers at once. That's fine. So we need to respect back pressure. How do we do that? With a promise. So on value, you cannot return anything. You can't return anything back to consume. What would that mean? Like, okay, I got some value, here you have a string. So it needs to return void, or an empty promise. So let's say that for every value we consume from this channel, we save something to a database, and we expect this function to return an empty promise. I promise that it's empty. That was not intentional, but it is empty, an empty promise. Just to signal that the saving is complete, it's finished. Okay, it's synced to disk and the database says, yay, it worked. Consume will not call on value again until this promise that this returns is resolved. So now you have back pressure. If this is slow, then, well, it's not going to happen more than once at a time. And then it's up to you to respect back pressure when you write things to the channel, which I don't have time to show today. Maybe some other day. It works. I promise. Sorry. Shouldn't have. So that's all fine, but you can probably do more than one save to a database concurrently, like at once, I think. Usually. Databases are kind of good with that. So, as an example, if we saved a database, how could we allow more than just one of these functions to be running, whatever that means, before we wait for it and call it again? Well, scroll bars, I figured. Scroll bars, I figured. You do it by providing an argument to consume, which is, for instance, concurrency. So by just saying, I use concurrency 20, it means that when it calls this on value, which will call save to DB, which will return a promise, it will ignore the fact that it's not complete yet. It will call the function again and again and again, up to 20 times. And then it will say, okay, now we need to listen to these promises and see whenever some of them are complete. Is this like super weird? Or we follow? Yeah, trivial. Probably easier than some of the sphinx. Underneath this, there is an enormous amount of sphinx. And I actually learned a few things from the last slide, so I can do it even better now. Actually, probably more than 50% of the code is sphinx, actually. Maybe like 70%. But this is pretty cool, I think. This is usually not that easy to solve with normal code, consuming things with concurrency and handling this as easy. You could specify not only concurrency but queue, so you can say consume on this thread pool with concurrency 16, and it will just fix everything for you. And where are the mutexes? Well, yeah, they're somewhere inside. Time-wise, I'm better than I expected, which means we can talk about something really important after you have written code before you run it in production, which is testing. If you would choose to use this library, which I wholeheartedly recommend, of course, because primarily it handles exception safety very well with asynchrony. That's maybe I didn't say that, but that's the most important thing. Exception handling or error handling is really hard with asynchrony. Then you need to test your code. So, kubetest is a small library, which is Q, of course, and Google Test. Does anybody know about Google Test? Everybody's nodding, cool. And it's making unit testing asynchronous code trivial, and I swear, I didn't use that word. This is a Google Test unit test. those of you who have not seen Google Test, it's still obvious. You create a test function called myTest with a category or fixture. You do something, you expect this function which says should return 5 to actually return 5. Otherwise the test fails. Is unit testing asynchronous code this easy usually? I think Björn knows. It's not. You need test fixtures, you need to create like phony fake functions which you expect to be called. And if they're not called, then not good, and so on. It's tricky. With qtest, you include 2 headers, and then you have this qtest make scope, which creates a test fixture. Does anybody not know what that is? If so, good. Don't learn what a test fixture is. You will write better unit tests without knowing. You will write very complex unit tests if you know. And complex unit tests are bad unit tests. Because then it's hard for you and your colleagues to know what the unit test is supposed to test. If you don't understand the test, and you will not understand the test if that's the case. That's my own opinion. That could be wrong. So in this case, we're not calling a function which returns an integer, which would be easy. We're calling a function which returns a promise to a string. And then we take that string and return the size. So that expression, the size, the variable, the size will be a promise to an integer. That's standard size t, which is an integer. So we would like to know that this future integer is supposed to eventually be 5. That's what we want to know. Is that the case? We can't use expect EQ, can we? No. Expect EQ is the normal Google test macro. This is not my invention. Expect true, expect false, expect throw, all these fantastic things. But with qtest, you have some macros, the same as Google's, but eventually expect. So basically, it allows the first argument or second argument or both or none to be a promise. It's completely like value or promise agnostic. And it will await the promise, if it's a promise, before the test completes, to ensure that it will become an integer to begin with, or something that is comparable with an integer, and that it is 5.
So what does that category object contain? Is it a queue?
It's a lot of stuff.
Yeah.
Do we get this question? That's a good question. What does the fixture contain?
Yeah.
Queues, a thread pool, a blocking dispatcher, and some code.
So when does it start running? Is it from the first eventually expect?
It kind of intercepts Google tests and does things before this runs, and it does things after this runs.
It's complicated.
It's a little bit of code.
Yeah.
And these macros are also a little bit of code, with probably like 80% Svinay. But it works. And the code is not super complicated, so if anybody wants to participate on this library, then feel free to. It's GitHub. So basically that's it. Promises make your code smaller, more easy to understand. Asynchronous flow is as trivial as synchronous flow. Thread safety without mutexes. I think it's worth looking into. That's all I had to say. Thank you.
Question? I have a question about exceptions. Could you rewind back to the actual code example? You had everything in int main.
Int main was probably where could that have been?
Where you had the actual queue running. Like a complete example.
Oh, int main.
I think you had an int main.
That's a stupid code. I mean, that's a silly code, I think.
Well,
maybe
you had your queue and you called run on it.
Yeah, start, I think.
Start, yeah.
It's fine.
What happens with if someone throws an exception? How do you see it? Where do you see it? Maybe it's a stupid question, but
no, it's probably not a stupid question. It's probably here.
Yeah. So say someone throws an exception inside somewhere there. Where do you see it?
Where do you see where someone throws an exception? That's a good question here. For instance, BD start. That starts that starts a dispatcher, which will call functions.
Yeah.
And that's the thing is that all your functions are ultimately called by Q.
Yeah.
So the only function you perform is this in your whole program, basically.
So if you wrap that in a try catch, then you're gonna get your. If you throw your own struct, is that where you catch it?
If it's the last thing you do in your code, yes. Otherwise, where could that? Otherwise, usually like this. Usually, I mean, you probably want your whole code base to be using promises.
Yeah.
So you write code like this, and then this function. I can't even mark it. Yeah, I can. This function throws an exception.
Yeah.
This will not be called. It doesn't have an argument to call it with, and it wouldn't be nice to call it anyway, because what would that mean?
Mm-hmm.
This will not be called either. But this function might be called, if it was this exception. And then you can do whatever you like there.
Yeah,
Quit the program.
Yeah, the exception is caught there, so it doesn't.
Yeah. Exactly.
Yeah.
Exactly. So there's no exception leakage,
No.
basically. And it also means that when you write code, functions that are not supposed to actually handle exceptions, they will not handle exceptions.
Mm-hmm.
They will just return a promise, and then you let someone else handle it. That's a big benefit, I would say. Otherwise you spray around lots of things like this. Okay, so this particular thing failed. Okay, so like, what are we supposed to do? I don't know. How would you... Okay, so this isn't a function, so probably you need to propagate this error somewhere. That's quite nasty. Because if you have a synchrony like this, you're basically forcing the outer function, which is not shown here, to also have some exception callback argument that it will call to signal upstream that there was an exception. But with promises, you would, if this was promise-based, this function would just return that exception right here. And everything becomes like left side.
Yeah.
I'm not sure if I explained that.
I think I have to do some experiments.
Yeah. Fundamentally, it's about being able to write code like this on the left side.
Yeah.
And often, in these functions, you don't have try-catch. You just allow them to crash and let somebody else deal with it, whoever called the function. You don't have try-catch in every single function in your code, usually. And the same with promises. You don't handle fail in every single function you have. If something fails, you will just return that promise, which will contain the exception, and let upstream handle it. So the code will become as nice and beautiful as we're used to with try-catch. But yeah, maybe this is a little bit new to many people, so you have to play around with it. You can make mistakes with this programming too. But I think generally the code will become better. There was one first.
Okay, just a quick question on the exceptions. I guess you catch them in your framework down somewhere. Do you catch all types of exceptions, or is it some kind of subsets, like standard exception?
Do I catch all kinds of exceptions in the library? Yes. Yes. Because I catch them exactly like this. This is the code that I do exactly. It's catch, ... So, I mean, if you are a bad citizen and you throw 5, some people throw like integers and stuff, an integer is not an error. I will rethrow it back at you. So then you have to deal with it.
Just curious.
So I do catch dot, and I do take the current exception and just rethrow that. So yeah, good question.
I was just wondering, this library, the user of it is relieved of a great burden. The Q library takes care of it by carrying the burden itself.
Yeah.
How have you tested it to ensure that it is correct?
Have I tested this library to ensure that it is correct?
I assume you have. How?
You assume I have. Well, I do my best. There are unit tests. It's not like an insane amount, but I think I have like 200 plus unit tests, where I try to test as much as I can, yes. It's a big thing to do. But these tests cover like most things you would do. I haven't run any code coverage things. It's very easy to set this up in your compiler. It's like C makes some yada yada done.
Yeah. Now
So if you have such a tool, I don't have that tool.
I was thinking, like you mentioned earlier, that it's notoriously difficult to test threading.
Yeah.
And you take care of it. So
It's horrible to test threading, and I take care of it, so then the burden is on me.
Yeah.
Yeah. But it's open source. So the burden is on anybody who wants to help out, basically. True. But, I mean, I have run these unit tests so many times, and they work. So, I think it works. It's a good question. I don't have a good answer. Because testing threading and asynchrony is... it's just super hard.
Is it being used in production?
I don't know. Is it being used in production? I'm repeating to the microphone. I don't know if it's used in production. The people who made this game last summer reported it to Android. I don't know if they use it. Maybe they do. It has some stars on GitHub, and I mean, every star in a C++ project, I think, means like probably 100 people using it. In JavaScript projects, everybody's like starring everything, but C++, it's not. We don't have that community, I think. So with these, I don't know, 20 stars something, I think people are using it. It's a bit scary, but they do, maybe. And I have gotten some issues which is fixed, so I think it's used. It's not big yet. Maybe now it will be. And well, I'm a programmer. If you need me to test things in your company, we can maybe solve that. But it's not big yet.
Okay, yeah, obviously a question about this, your all function. Did you consider, or how do you motivate this? There is also this school of thought where you are not, where you constrain yourself to a single argument in the pipe. Here you unwrap it to 3 arguments here. Did you consider turning that kind of stuff into a tuple or something? To maintain a single argument.
Could this be a tuple when you have this function instead?
Yeah, because now you have them with 3 arguments.
Yes.
I mean, you can have it, but you can have pros and cons there.
You can have both. With a quite insane amount of spinning. I mean that. You can read the code and disagree. You can do both. So this function can take 1 argument, only taking a tuple of these. That's fine. Which makes it easier to meet a program and do library things on top of it.
But the library right now would have handled the tuple there.
Yep.
So, okay. No, it's okay.
Yep.
I just had a comment. If you break the code, you will know who uses it.
Yeah. If I break the code, I will know who uses it. Yeah. I'm not that brave. Sorry. Because maybe somebody's using it.
I was thinking about this example. Since you have the 2 promises, one takes 1 string and one is an integer and a float. Is it possible to express the continuation, that then to have 2 parameters? One is a string and one is a tuple of int and float.
No.
Okay.
You cannot do anything you like.
No.
But it's interesting because this example shows you where both these promises succeed. But sometimes, out of a lot of things that you wait for, one thing might fail. And then this function will not be called. Because it's then. Then only is called if the promise is resolved. successfully. If any of the promises is rejected with an exception, you will have to search for the .fail, which you don't see here, which is somewhere in the code, hopefully. So what you can do is that you can call the function here on the promise called reflect, which will turn this into a promise, from promise of string into a promise of kind of itself. So you can introspect it. So then you will get then with all these promises, more or less, not really promises, but something else with another name.
Meta promise.
I don't need to confuse you more than necessary. So then you can look into these promises and say, did this succeed, did this fail, did this succeed, did this one fail, when all of them are failed or succeeded. So that you can do. So you can handle them one by one, yeah. There is no Q sum. This exists in some other, mainly in JavaScript libraries, which is also cool. Like continue whenever any of these are finished. I have never had a use for it, so that's why I haven't implemented it. I think the use case is a bit weird, but that could have been added too.
Yes, I have a question about terminology, which I'm always need to know. So C++ 11 introduced something called a standard future.
A standard feature.
Yeah, right, which is kind of similar to this, but
Yep.
it doesn't yet have this nice functionality that you can change them and compose and so on. But it's on the way, it's coming somewhat sometime.
Hopefully.
Yes. But then they also have something called a standard promise, which
Yep.
is like the thing that puts a value into the future on the other end.
Yep.
But then, like you said, like JavaScript has promises, which appears to be kind of like this and kind of like features.
Yeah.
But like, who is using the right word for this and where?
I'm using the right word for it.
So the standards committee is one.
The standards committee is a bunch of really good people, but
Like, why do they get this?
I should mention that there is a person who is responsible for this library as well as me, which is U1. Where is he? U1 is over there with a hand up. I would not be here talking about this without him, because he wrote this library before me, but it wasn't called Q, and it wasn't called promises either. And not futures either, for that matter. Handles. Yet another fantastic name out of all fantastic names. Promise, handle, future, asynchronous task, whatever. So he wrote a library basically exactly like this. I helped out a little bit, like some percent. And that's where I got the inspiration from. So it's thanks to U1. It's absolutely the case. And then I quit that company and started doing JavaScript. And at that time, JavaScript that's when promises basically came into the language. And the whole community changed. And I realized, these promises are nice, and the API is nice. And U1 did the same thing in C++. So I took his ideas and Fnei knowledge, JavaScript terminology, and fused them. So you should blame JavaScript. There was something from
Yeah, back to when you have multiple you're waiting for. Whenever everything is okay, you're waiting until both more or less returns. But if you fail with one, will you return immediately, or do everybody need to return something before you can actually start looking at this?
Good question. If any of these fails, then what happens? Can you get notified of this immediately or not?
Yeah.
Or do you have to wait for all the others to finish? You will have to wait for all the others to finish. Yeah. I can't right here think of a better way than doing it manually. There was another hand.
Are you on top of the STL primitives like promise and
On top of as in knowing a little bit of what they're doing.
on top of us using them as your primitives? Are you on top of operating system APIs?
This is on top of C++ 11, nothing else.
Nothing.
I know a little bit of what they're doing.
Can
But
you
I'm
get,
faster than them. This
get
exists.
a stood
Yeah.
future out of your API somewhere?
Can.
Can I get a stood future out of your API?
No. Do I use stud futures anymore? I don't know if I do. I used to. I'm thinking of not using them because I don't find them very useful right now.
But
But they will.
If you need one to something else.
Yeah. To interoperate with.
Yeah.
Well,
Get native handles.
Yeah. Then you can actually very easily turn the queue promise into a stud promise and get the future from it. But no, you cannot get the inner things because I consider them implementation details. I might want to change them. So no. But it's good to know. Standard futures exist. They also carry future values. It's the same thing, but you can't schedule continuations on them. So if you want to know if there's something to do, you need to try or block or they're maybe good for something. I don't know.
But you don't have like P threads.
Standard threads,
Standard threads.
because we have it since C++11. It would be better if I based this on C++14 for my own sake, because they fixed a lot of things actually. But it's pure 11, which means that's why it's portable. There's no P threads. Kind of. I think debugging is quite important. So I have code which takes stack traces and names threads. This was maybe not obvious, but it's quite interesting. Where was this? Where was my main? Holy shimoli, it was this. So when you create a blocking dispatcher, you need to provide a string. That's kind of weird. And when you create a thread pool, you need to provide a name and a queue. So on libq.io there's lots of tutorials to read what this means. But these names are actually names that I will name the thread. So if you break your code, the debugger will say pool 1/2 or 2/2. So you know the name of the threads. And the main thread will not be renamed, or will it? I don't know. I can't remember. So there are some P threads, Win32 things, Mac OS, BSD. Yeah, some nasty stuff. But it's to make debugging nicer for you. Cool. No more hands. Fantastic. Good. Next.